Assalamu alaikum all of you. It's our honor that we are inviting today Dr. Ghaffer Kiani for his presentation. Let me introduce briefly about him. He received his BS degree in electrical engineering from Islamic University of Technology, Dhaka, Bangladesh in 1997, and MS degree in electronic engineering from Ghulam Ishaq Khan University from Pakistan. And then he did PhD. He received his PhD degree in electronic engineering from Macquarie University, Sydney, Australia in 2009. And from 2009 till 2012, he was postdoctoral fellow at Commonwealth Scientific and Industrial Research Organization at Australia in the field of very high throughput communication system. He was over 13 years of academic and professional experience in the field of antennas and propagation power system, electromagnetics, RF and digital communication system. He is an expert in 2.5 and 3D ADS software. He is the author of over 60 high quality journal and conference papers, mostly in IEEE. While one of his research papers, he won the best prize award in a conference held in Gold Coast, Australia, which is related to the seminar topic today. Currently, he is an assistant professor in King Abdulaziz University, and his current research area of interest are frequency selective surfaces, which he is going to talk today. So, and other areas like artificial magnetic conductors and their application in antenna design, metamaterials, MEMS, NAMS, smart buildings, and very high throughput communication using THZ frequencies. So, I leave the floor for Dr. Ghaffer to start his presentation. Thank you very much.
Thank you very much, Dr. Moinuddin. Thank you very much, Dr. Moinuddin, and thank you to Professor Sagaf for inviting me for this presentation today. The topic of my presentation is energy and communication efficient smart buildings using frequency selective surfaces. So, let us start with a small graph which is taken by burning oil to keep cool, the hidden energy crisis in Saudi Arabia. This is an article written by Mr. Lan and Stevens and published by Chatham House in December 2011. According to this, if we look at the energy consumption in Saudi Arabia, and if the business is as usual, what will happen that around 2036, Saudi Arabia will become not an oil exporting country rather than oil importing country, because the oil is being burned so lavishly that if the measures are not taken, this is going to happen very soon, and we are already seeing price hike, petrol hike, and this is very alarming, especially to a country which is very, very hot. So, if this happens, which we say God forbid it never happen, but if it happens, what will happen in future? This is going to happen. One thing called load shedding, probably people are not very aware of this thing, load shedding. It's like power cuts. It means you have power for 1 hour, then 1 hour there is no power, because you know the oil, most of the generation plants here are oil based. So, if there is no oil, there is no generation, there is no power, there will be load shedding. And imagine in a hot country, living in a hot room without power, how will it be? That also means that there will be a reduced industrial growth, because industry is run on the power, and if there is no power, there will be no industrial growth. This is already happening. This thing we know already happening. The petrol prices will go so high that the cost of living and cost of other things will become very high. So, it will also be a big problem. And this also a most probable chance that while the temperatures are in 45s and 50s and there is no power and there is no air conditioning, this might happen also. So, this is the background that what will happen around 2030, 2035 or 2036. Okay, we leave it there now. Have a look at this building. This is the Oracle headquarters in California, USA. This is Macquarie Bank building. I took this picture in Australia. This is the picture. This is the Intel headquarters at Santa Clara, California, USA. This is Nokia headquarters in Finland. This is one of the beachside smart home in Australia. I took this picture. This is a train. This is the real one. This one is the real one. And this is a future bus or a train which will have this sort of structure. So, I have a questions to audiences. What is common in all these buildings, homes and trains? Can somebody tell me what is common there? Glass. The building is made up of glass, not concrete. But this is not an ordinary glass. This is energy saving glass. All right, now let's go to the next. This is how an artist portrays the future of our cities. This will be the cities in future. Mostly the building architecture will use glass, energy saving glass in their architecture rather than just normal material. Now, according to International Energy Agency IEA, it is predicted that world primary energy demand can increase by 40% in 2030. And that is what is the prediction about Saudi Arabia as well, about 2036. This is going to happen. And in United States Energy Information Administration EIA, they said that $107.9 billion are annual energy cost of commercial buildings, not the household, the commercial buildings. This is what we have, and you can see how big amount this is, $1 billion. That means 1,000 buildings use 1 million kilowatt hours of energy per day. So imagine if we keep on going like this, what's going to happen in near future? From Australian perspective, Australia is the 16th, is ranked as the 16th high energy consumption country. And they say that in 2016 to 17, the energy consumption was increased by 3.5%, which is a very big amount. I come back to my first slide, that according to this article and the prediction made by these two guys, 2036 around here, Saudi Arabia will become a country with oil import rather than export, and that will have the consequences which I already explained. Okay, now what are the possible solutions to this energy crisis? Number one is called the capability enhancement. Capability enhancement means install power generation like wind, hydel, nuclear, natural gas. Also the reduction of power losses in the lines, transmission lines, long lines, we can reduce them down and we can create more power to keep going. But the problem here, because in Saudi Arabia, most of the power is generated by the oil, and if there is no oil, then they have to have hydel, solar, which will take time. They don't come very quickly. So even if the government, like 2030 vision, if they start now, it will take a lot of time to bring this power into the system. There is one saying, they call it energy saved equal energy produced. If we save $1, that means we have earned $1. So the other techniques which can work straightforward or straight away, this is called energy saving techniques. So we can use energy efficient appliances, inverters, we can change these bulbs with energy saving bulbs. Okay, we should not use energy during the peak hour, use it when there is people are not working, or in the midnight when nobody is doing something. But the last one here is the energy saving glass in building design. And in my traveling around the globe, there are countries which are very hot or very cold, and this is what we need there. You see the Arab, this is Emirates, they are very hot countries. If you go to the Europe, they are very cold. And if you look at the building design there, most of the buildings you will see they will lose a lot of energy saving glass in this design, in their design. So, here it is, as I explained, we can, if you go to the market and you see 5 stars here, that is a good one, it is saving energy, or use an energy saving bulb, a high quality, it will reduce the consumption. Do not use this bulb, they use a lot of power, or we can put solar in the home and even in the industry. But what we are discussing today is this one, that this is an energy saving glass which you put in the windows or in the architecture, and that will give you a lot of saving. Now, what is the difference between a normal glass over there and an energy saving glass? Normal glass, this one, but the energy saving glass has a coating, very small coating, thin coating of in the dimensions of nanometers, very thin, on one side of the glass here. So, what this coating does, when the wave comes from here, thermal heat, it will stop it, it will reflect it back, it will not let it go in. So, imagine if this is a room and this is all glass made, we run the air condition for 1 hour and then close it, and because your building is energy saving, it will last for 3 hours, you do not need to run AC all the time, otherwise you keep on burning the energy and it is going out. There are 2 types of coatings. One is the hard coat, the hard coat here, and one is the soft coat. I will explain them, the two both have the difference. Now, the hard coat is like a single glass, like this TV, single glass. It means that if somebody go and touch the hand, or if somebody go and rub, it will not go away, it is like a metal. But for the soft coat, if you go and touch, because it is oxide, it will go away, it will be damaged. So, what they do, they put 2 glass, one glass here, one end, and put invert inside, and then it is put inside some sort of packing, and then they put it 2 glass or 3 glass, so the people cannot touch. Both have pros and cons. Okay, this is what a factory called Pilkington. Pilkington is one of the best energy saving glass company in the world, and I visited them, and this is how they produce the glass. Basically, you can see the glass is going through the chamber, and they are putting this small metal or metal oxide on one surface of the glass. So, this is the scenario. So, this is the window, this is our energy saving glass. What happening? We can see through. So, in the visible spectrum, the light is going through, there is no problem, we can see through the glass. Also, the sun, when the heat is coming, it is striking here on the surface where there is a coating, and this coating does not let the heat go inside and it reflects back. Also, if you have a Wi-Fi here inside, which is 2.45 gigahertz, we do not want this Wi-Fi to go outside and somebody detects your data, it will also block it and put it back inside. But there is one problem. The problem is this one. In such a building, if we go inside and we have mobile phones or some other communication system, this coating will also block this communication, which is a drawback. This is a big problem. So, how to solve that? Before we go there, this is one of my research in Sweden, and you can see this is an energy window here. We have these 2 antennas, and we are sending a signal from here, measuring the transmission of signals from 800 megahertz to 6 giga, and we know a lot of our RF and microwave, they are in between this. So, we have 900 megahertz somewhere here, then we have 1800, 1900, all this, and we can see that about 30 dB loss is here. So, it is stopping all the signal by 30 dB, which is a big loss. So, this problem of the signal going through, we can solve through a technology called frequency selective surface. Frequency selective surface are what? They are actually like a filter, but in the space, not in the circuit, and they are basically periodic structures which are put in a periodic x and y directions. Like here you can see there is a periodic structure here, this is, you can see cross dipoles here, this is basically an FSS structure, and according to the frequency which we design, it either pass or stop, and there are actually 4 spectral responses for the frequency selective surfaces. The first one here, this is the band stop, these are the patches actually. So, you can see this is basically 2 2 by 2. If we make the complement, so this is the metal and now this is the aperture inside here, this will become a band pass. This is a band stop, this is the band pass. If we have the patches like this in an 2D like an array, then we can have low pass, and then if we have a complementary, we can have a high pass. So this is, there are 4 spectral responses as in any other case. Now, to give an example to you about a frequency selective surface, have you seen the screen of your microwave oven in the kitchen? If you look at the screen, you will see this funny structure there. This is an FSS. If this frequency selective surface is not there, this 2.45 gigahertz will come out and burn your face. So it is basically stopping this. So this is basically a high pass filter. High pass means that this will go until 2.45 gigahertz and then start passing. So before that it will block all the frequencies, but we can still see through because the terahertz frequencies are still passing. If this is not there, the electromagnetic waves will burn us 2.45 gig. All right, here is another example. Do you know what is this? It's a stealth aircraft. So if this comes and attack our country, our radars cannot detect it. Why? Because the surface of this is designed using FSS, and FSS knows the signal, the bandwidth of the radar. So what it does, when the bandwidth comes, it passes through rather than reflect. You know how radar works. Radar sends the frequency hits and then it returns back, and once it is back you can detect on your radar. But once the frequency strikes here, and due to this FSS and called RCS, radar cross section, the frequency passes through this metal and there will be no reflections. So these sort of aircrafts can come and attack us and we can never detect them. So this is one other application of frequency selective surfaces. Also, if you look at this aeroplane here, this is called a radome. These aeroplanes communicate with the ground stations and with other aircraft, and they have antennas. We cannot put an antenna on the top because of the air, it will be blown away. So what they do, they put the antenna inside, and on this structure they create an FSS, and this FSS will only pass the frequency which is required, and the rest it will block so that there is no interference. So these are the 3 applications of the frequency selective surfaces. So the solution to the problem with the glass which has a coating, it is stopping the phones and there is no signal inside, and this is exactly happened in Sweden, where some people stood up and they say, we will not buy your energy saving glass because when we are in the building we don't receive this signal, that signal. So they gave this project us officially to do this. And you can see here with this machine, we are trying to create this structure inside the coating. You can see this one. So this is a dual band FSS, and what it is doing is that it is passing 800 megahertz and 900 megahertz. The rest it will block. All right. So
is the laser etching?
no, this is just with the machine. But I have the laser one. If you want, I have in my store in the lab. I will bring and show you. I wanted to bring, but I forgot before this. Anyway. This is one of the scenarios. Scenario number 1. This is a hard coat. This one of my students in Edith Cowan University in Australia. They have a building, and they had 2 towers, 2 mobile phone towers, Telstra, and you can see here there is one from Telstra which is using UMTS, and the other one was Telstra 3G, which with these 2 frequencies. You can see these 2 towers here. And the employees inside, they were fearing that these electromagnetics are coming and hurting our health. We will get sick, and you know these Western countries, they are very strict about these. So we took this antenna from where we can see the electromagnetic field, and we found that in some of the parts, the energy level was more than the recommended by the communication companies. This was more than that, and it was really a hard problem. So they asked us to change this glass, ordinary glass, with the energy saving glass. But the problem was, once we said that and they managed to change some of this glass, now they have a problem with the communication. They cannot get the mobile phone and they are always, you see. So then they gave us this problem to the student, and his master degree was basically on this topic. So what he did, he actually created this sort of a structure. This is, you can see this aperture here is for one band and this aperture here for other band. This is a FSS unit cell. So, you can actually multiply this direction and this direction. This is what we did. There was one paper also published, and this you can see in the CST Microwave Studio, the software which we use. If we put it on the glass, it will look like this. So, the bigger the glass, the bigger the structure like this. So, this is a basically repeated structure. This is called FSS. Now, once we simulate, you can see that at 900 megahertz is 100% transmission. Then it goes to about 1800 and about 2200, that is the frequency we are given. So, you can see at these two frequencies, this FSS is passing all the signal, 100% signal, but rest of here there is no communication. So, we provided this solution. We put the energy saving glass and we also put this structure on the top, and their problem was solved. So, these are the two, this is for the TE for transfer electric polarization, and this is for transfer magnetic, and in both cases we can see it is perfectly stable. There is no, here I have to mention that FSS is a screen in the air. So, the wave can come like this, it can come also like this. So, as the angle of the wave change, the impedance will change, and we have to design in such a way that even the angle goes to 60 degree, the response does not change. So, it is a very big challenge. One of our students here, he knows it is a very big challenge to design an FSS for a wide range of stability, polarization and angle stability.
You want to block the 2116?
No, we want to pass this because the glass itself has a coating, and coating is blocking everything. So, we put the glass so that have the problem heat and the problem with the signal is gone. Now, we just want to pass to some signals.
But you mentioned that they are scared from these two big antennas.
This is correct. Yeah, by this sort of design, we can actually make sure that how much amount we want to put it in.
Okay. So, you are passing it, but with a reduced.
Yeah. We know how much, and this is all this here. And it is not only these two towers there. There were other communication systems around there. So, we were getting a lot of signals strength which people were scared of. Even I saw a few people working there, ladies, and they just frightened up and they run away. They were saying, we will not sit here anymore. Okay. Now, that is the hard code. Now, this is a soft code. In a soft code scenario, this is again a soft coated glass, and we have a cross dipole here. This is the etched, signal is going through from here. This was Pilkington HP Suncool, this is a trademark. This is one of the glass which Pilkington creates. So, you can see by in the simulations, if we have the full coating, this is the curve, and we can see at 900 megahertz about 30 dB loss. So, the signal is not going through. And here even at 1.829, you can see it is a lot of loss. So, what we did, when we create the cross dipole, now you can see with the dipole FSS, now we have improved here about 20 dB improvement at around 1.2, but you can see at 900 megahertz we have about -11, and at somewhere about 18 here we have 20. So, this is the improvement here, but there is a question why we are not getting a very high level of improvement here. Why? Because it is made up of oxide, and you know the oxide is not perfect metal. So, if there is no perfect metal, there is no more electrons to move. So, there is no high resonance. So, we do not get too much. But in this scenario, if you look at 2.45 giga here, we still have a very good communication stoppage here, because we do not want 2.45 to go out of the building. In the previous design, if you look, in the previous results, if you look at let us see at 2.45 here, this is 2.45, look, it is also passing 2.45, very not too much, but lot of transmission is going through this one, which is not required. We do not want it. We want to save our data from the outsider to breach into our system. Now, here is the measurement setup. You can see here is we created a metallic sheet so the signal doesn't go through this, and we put the glass. You can see here is the glass and this is the coating on the top. There is nothing inside. And if you go to the next one, now here you can see the same glass, but we have now etched this one. There are 2 by 2 cross dipoles here, and now we are mirroring again. So there are 2 scenarios. One scenario where we have only the glass, and then when we have etched a 2 by 2 FSS, and here is the result. And you can see, if we saw the theoretical result, the simulation, the measured results are in agreement with the theoretical results. Okay, now there is a problem with the etching. So for example, if this is my glass and this is the coating, if I take etch here, if I make a structure here, there is a drawback. And what is that? The heat will go through. So for example, if an energy saving glass is giving you 80% heat loss saving, if I create aperture, lot of apertures there, it means I am removing the coating. So if the coating is removed, that means now the more heat will pass through, which is not required, because some companies say no, our heat loss is now more because of this structure, blah blah. So now we have come up with another solution, because energy saving glass is very expensive. Number one, if we buy an ordinary glass, an energy saving glass is very expensive. Number two, when we have the glass, now if we have to go and etch, as you have mentioned, it's very difficult to have a big glass under somewhere and they do the etching. So we come up now with another solution, that is, just take, okay, before we go there, yes, here I have to explain now. So you can see this is a spectrophotometer which can actually measure for your UV and visible and near infrared. So when I went into the factory, my FSS which you saw here, the FSS which you saw here, you can see how big this size is. So I took this one and I took this one, these two, and I thought that I will go and do some thermal analysis. But what happened, when I went into the factory, they show me this machine. They say we can only put a small part here. So it's a big challenge now. How can I measure how much loss happened because of my aperture? So I come up with another solution. I asked them to give me a glass of this size with a coating. Then what I did, I took first this area out. So first I measured with the whole glass with the coating. I saw how it affects. Then I took this one out, and then I saw what happens. Then I took a little bit more area out to see the amount of area removed is how it is related to amount of heat loss. And we come up with this. If you see here, this is the one of the glasses. You see when it is ordinary glass, the ordinary glass curve is this one. We can see through the ordinary glass, the visibility is very good. And if you look at the thermal infrared also only 20% heat is stopped here. If you put a glass in a window, definitely it will stop something which is about this 20%. But when we put the coating, now you can see the visibility is little bit down because of the coating color. And also if you go here in the infrared, you can see about 80% heat stoppage, which is a very good thing. So this is with the full coating. Now when I take a small area out, I see when I took the small area out, there is a heat loss here, because now it was giving us about 80% here. Now it is giving me maybe about 78 or 77%. So there is a loss here. Then if you go here, you can see when I took another area out, the efficiency is going down. It's going down and down and down. And when I plot it against here, you can see at these frequencies here, 700 and 400, there is no change, because it's a glass, so glass will not have any problem with the viewing. But if you look at the infrared where the heat is, the amount of percentage removed is actually linear. So what is the bottom line? Bottom line is, if we remove 10% of the glass, there will be 10% heat loss. Heat will go through, which is not good thing. So to encounter this problem, this is our current research now, and I cannot give too much information on this because it could go into a very high level of journal. It has never done before. So what we are doing now, instead of buying an energy saving glass, what we are doing, we are getting an ordinary glass, normal glass, and then we are etching FSS, copper FSS on the top of this, and this FSS has a response in the infrared region. So it will stop all the infrared. I will show you now how. We have the simulation results. We are going into the. So how many of you have heard about ITO, indium tin oxide? You see glass with indium tin oxide. This is a very popular sort of thing which people use for a lot of applications. It has a coating called ITO. If you simulate ITO, this is actually measured. We did the measurements here. If you look at the ITO curve, you see at around the visible spectrum, it has the full, you see it is going almost 95% viewable. But if you look at this heat side, it is not stopping too much heat. So we were trying to do first with the ITO, but the ITO did not work. For the glass, just data 1 is just the glass. You see through the glass, all the heat is going through. Then we did with the copper, and we did the cobalt. You can see the copper is the one which is having the high heat loss. But the problem is, you can see there is no visibility. So it means that if we put copper on the glass, nobody can see through. So now we are making a band stop FSS on this glass. How? Here. I don't want to give the dimensions, but only give a. So this is my FSS now. This is the glass, and these are the copper. This is the copper here. So this is a patch in opposed to the other design where we already have a coating, and within the coating you just put the apertures and the signal goes through. In this case now we are stopping a band stop filter. This is the band stop, and stopping what? These are basically in the nanometers, very small. And what it is doing, it is stopping, you see here, all the infrared in this region is being 100% stopped. This is a 100% infrared efficiency. The only problem we are still having here is in the viewing here, where we have to go through the visible spectrum. We want it to go somewhere here, which we are still trying. You can see we are from here to here, we are trying something. But at the moment, because we are doing this one, and we have got 100% efficiency with this one. And one of the good thing is this one, the future research, we can say that when the heat is dissipated here, we can actually connect these ones through thermistor and create energy. So the amount of energy which we have stopped, we can put into the power.
Energy harvesting.
Yes.
This is done by gluing these things to the device.
Yeah, we have to spray or something like this.
Yeah.
Some sort of spray system. Yeah. So this is now, these are basically the simulation results. Inshallah, we are now doing in the fabrication part, and if it is done, probably we will put it into a very good journal, maybe the Nature or somewhere, inshallah, because we have not seen this until now. This is a very new idea.
How stable is this one?
This one actually been done in KAUST.
Yeah.
And because there is one specialized team there and they are doing, we are not expert in that.
So that's what I'm thinking. You're doing inkjet printing.
Something like this, something. I cannot exactly, because there is some guy there, they are expert, they are.
Yeah, okay. Because this is the first thing you came to know.
Yeah. This is, but I think what you are saying is correct. Something like this. So hopefully when we get this one, we will do some measurements, and probably if they are closer like this, inshallah we will publish. So conclusion, energy problem, 2036, power goes down. Not even in Saudi, everywhere in the world. So we can create more energy. There is one solution, but it takes a lot of time. If we start project now, it will take maybe 10 years to make a power station. So energy saving glass can be used to save the energy instead of creating. It will take a lot of advantage to the country. It will take a lot of energy, and it will maybe advert the crisis. The solution is put an energy saving glass, but it has a problem. The problem is it also stops the useful signal, no signal for STC and other signals. So then you can create frequency selective surface inside, but it also has a drawback. That the drawback is that the aperture also removing a lot of heat, which is not required. Then we have come up with the copper side infrared band stop FSS, where we are blocking all the infrared spectrum, and we are trying to achieve a very good visibility through this one. Thanks for your attention, and now if you have questions.
I have several questions.
Yeah, please.
Any questions from
Yeah, there one. Yes. What?
Assalamu alaikum.
Right.
Regarding your experience, is there any applications of buildings in Saudi Arabia using these techniques for saving the power?
Not yet.
Not yet.
We are trying to have written a CAXT project where we are trying to advise to the government to put this thing in the building laws, because if it is not in the building laws, the constructor will never use this.
Nobody will pay more money.
Yeah, because here traditionally, if you look at the buildings, this is a tradition, like the windows are very small. They are trying to reduce this heat problem with the small window, but they think that the heat is not coming through the material, it is also coming. So I think it should be coming through the government laws, which they can put in the building codes, you know, the codes, building code, then it probably will come, inshallah. I have seen some now buildings in the Jeddah city, they are using a lot of glass. So that means that lot of people now may be realizing this.
Thank you.
Assalamu alaikum. Thank you very much, sir, for the presentation. I would like to ask you, in developed countries, by what time period do you think this technology will be implemented?
In developed countries, this is already implemented.
Already implemented.
Yes. If you go to the very cold, like you know, Sweden,
Okay.
France, Germany, even Russia, it's -20, -30. All the windows which I have seen there, a building,
Okay.
they use already this.
And in the Middle East?
In the Middle East, only in Dubai, some commercial buildings.
Okay, fine.
But they are, because of, you see, the power problem here is people never saw it, so they never think it until it happens.
You're right.
So probably with the passage of time, people will realize. We are also trying to make to the government realize that this is a problem. If they start it now, probably in 10 years,
Okay.
they will have a lot of fruit out of it. Plus the building looks beautiful, you know.
Yes.
I showed you the buildings, all the buildings in the world, you see, they are fully glass.
Thank you very much.
Any other questions? Actually I have actually a few questions, and of course, you know, coating is used. Actually, at my house, actually, I have a thermal coating.
MashaAllah.
So it's already used in Saudi Arabia. They are using spattering, the big coating machines for glass. It's used in several companies here. So it's a very already used in a lot of buildings. Actually, of course, they are using double glaze, and then in one surface they have this coating, some sort of coating. Now the question is that one issue, as you mentioned, is that by etching you are really removing the coating. But what about if you do the etching and then do the coating later on?
It will come back to square one.
Because of the no, but still you're doing that. The special, I mean, the purpose of this is that this structure is doing the I mean the filtering in a sense, because basically
it is passing. Yeah, the etching is passing. But if I put another coat, the coat will again come on the etching.
So basically, okay. So
yes, it will
not work.
Yeah, it will not work.
Okay, I see. So basically, you have really to remove the material. You have to remove the coating.
Yeah, we have to remove it.
Now, the other question is the following. We have actually three conflicting issues. They have energy saving glass, which does what it's supposed to do. It does reflection. One point, maybe it's related, you want to do energy harvesting by this. And the third important point is the solar panels. Nowadays there are clear or solar panels where they can generate electricity. And they are, I think I forget now, the technology is called crystal, whatever, I forget now. And I think this is a very hot area, and you can have inside panels, outside panels, and you can really make a, and okay, how this fits with that. I mean, there are so many things. Of course, you know, if you could get solar panels, of course, the solar panels, they are very important. They need this IR radiation definitely to generate the electricity. But on the other hand, also you want to reflect this. And of course, if you can reflect some, I mean, there is some sort of...
yeah. You see, the solar panel is from generation side. Glass is from saving side. So generation, yes, as I said, we have to put even windmills. And I see that Saudi Arabia is taking very good steps in this direction.
What I'm saying is that nowadays, actually, we do have glass panels, and some of these buildings, these glass panels could be solar panels actually, the new technology actually, and you can see through actually. They are not like the old semiconductor. They are, maybe we can talk about this later, and I'm sure there is a sort of
But are they passing the RF and microwave signals also?
I don't know, this is, I'm not sure, but the visible, yes.
Yeah, visible should be okay,
Yeah.
and also the thermal
But
okay.
I'm trying to see that because, of course, if you can generate electricity by this, and also you can not let some of
Yeah,
these
this is a very
radiation
good
get
one,
in,
yeah.
then you have really a
So,
perfect solution.
yeah, it's
in
a very
sense.
brilliant question. I mean, if that coating is not even stopping your RF and microwave, this is 100% best idea. You don't even need to do then all this research. It's just the one coating, and it will pass the infrared, it will pass the RF, and it also generate the energy. It is being done by nowadays, I have seen. But in my knowledge, most of these structures are doing like this, where they have actually patterns, and these patterns like antennas, transmitters, and because of the heat energy which is dissipated inside, they take this energy and then they have these converters from heat to power, and they are also creating power.
Okay. The other solution that you mentioned, so if I want to put it in my own language, is that basically, in a sense, you have this glass, normal one, and then in a sense, you put a metallic layer, in a sense, with some patterns, which is really your antenna, in a sense. That, am I right in
Yeah, that will be. But the size at that high frequency is in nanometer. It's so small. Probably with the naked eye we can't see. So that's how we can have a very good see-through effect, and also effect. But there the challenge will be with these very small lines, how to connect physically and things. That will be a different
But
challenge.
then actually, when you mention, I don't know, I'm just thinking how, if you want to, you're talking about nano and technology, I think that Shamim and the others are using with this ink printing or something, with antenna printing. It's not in the nano scale actually, it is the micro.
Yeah, that's a micro, but they have another lab where they do in nanoscale.
Yeah,
We can also do in our
That's
university.
what I mean. If in nanoscale, we have our own nano center actually.
Yeah, we have.
This can be easily done here actually in the nanoscale.
Yeah. The results I showed for the copper and cobalt, actually we did it here. We did the spectral, yeah. But there, I think there is some problem in the machine. One of the bulb, they said there was some issue with the machine or something. That's why we have to go there.
I see.
Yeah. So, but we have better machines actually here. Okay. If we want to do.
You mean
this.
in the nano you're talking about?
Yeah, nano,
Yes,
nano center.
Okay, and Dr. Main, yes, sorry.
First of all, thank you for a very good, nice presentation. I want to ask regarding the structures you mentioned for these filters, special filters. You mentioned some specific shapes in order to design some kind of filters. So the first question is that, are these the only specific shapes to achieve these kind of filters, or somebody can design any shape? And what is the, if it is yes, then what is the criteria to design these shapes?
Yes.
This is the first question. The second question, these shapes, the dimension of these shapes, meaning what should be the length and how much we put the dimension. Is there any calculation for designing these shapes, or these are just experimental,
Hit and try.
No. So
these are the empirical formulas.
Empirical.
Frequency selected surfaces. So this is basically lambda by 2 half wavelength dipole decay, and then you can just repeat it. The first question is, yes, there are
shape,
maybe 100, 1,000 different shapes. Each shape has its own pros and cons. If you need a, for example, a narrow band response, normally the cross dipoles sort of products are very good, these elements. If you need a wide band, then the loop type like square you saw, you can also use circle, you can use an hexagon, you can put a tripole, a lot of other. So it depends on the application which we know, what bandwidth we require, and what also the angular stability. When the wave become here, the signal will not be the same, you see. So normally the loop type, if you have a loop, you can pack them very close. So the closer you pack them, the higher angular stable they are. So in our case, because we need a higher angular stability and we need a lot of bandwidth, that's why I use the loop one, which is actually, you can see the square loop.
shape, yeah.
If I make it circle, we cannot put very close together. Probably I can convert into a hexagon. Then hexagon, we can put every side. It can even more.
So the more condensed, it's a better.
Yeah, the more condensed, the better. Yeah. better they are, their bandwidth is higher, and plus they are very stable with the frequency and also the polarization.
So basically, it's like a database of you pick from.
Yeah, it's a database. Yeah. There are. This is very standard. I mean, frequency selective surface books. There are a lot of books. They have this, but they are empirical. They are not hard and fast rules like antenna. Then you have to do a lot of, like you yourself. You do the algorithms.
Yes.
We also run these algorithms in our softwares and then find the right solution.
Right.
But at the moment, for us, just to give an idea that instead of having a very expensive coated sheet and then remove something is difficult,
Can do something.
just put another thing on the top and ever harvest the energy, and it's cheaper. The price will go maybe 100 times less, because energy saving glass is very expensive considered to this. But if we do this one, just take an ordinary glass and just put the copper. Copper is also very, cheap material.
Actually, related to the question of Dr. Mohammed, I mean, I know what he's thinking. Is that with this design
Can be optimized.
Sorry?
Can be optimized.
Can be optimized, because the way you look at it, it is a repeated structure.
Yes.
And then if I look at it, just common sense said, well, a repeated structure, maybe it's not optimal. Maybe it's a suboptimal. Of course, if you want to optimize, then you get maybe a crazy configuration.
Organization of these
Yes.
shapes.
That means that every area I have to do analysis.
Very good question. But you see, in this I tell you one thing, that the softwares, instead of they have, say for example, I have a structure which is 100 by 100. But in the software, what they do, they don't optimize 100 by 100 things. They take a unit cell we call it, and they put a boundary for infinity. So if I have to optimize, I just optimize that one cell only. And because it is repeated, and the boundary condition in the software says it is a repeated infinity thing, we have to only optimize one structure, which makes it very easy. And these algorithms, which Dr. Moin also works in, there are a lot of incorporated in our software as well, which we can run by one by one, and we can get the optimal solution which we actually want.
So basically, you're saying that this repeated structure will do the things optimally. Is this what you're saying?
Yes. If we define one cell optimal, the repeated will automatically be the optimal one. Because otherwise, if we simulate a glass of this size, the software will crash.
Yeah. From a theoretical point of view, yes.
It's a very good question.
Yeah. Point of view, and there is a practical.
Yeah.
I mean, if I want to do the huge optimization and using a supercomputer to do this, and then I end up with having
a problem, and again you go.
Another problem. I mean, an increase of 1% and a cost of so much, then it is useless actually, of course.
Yeah.
But just to see from the
simulation point. So that's why these simulation software, they are very intelligent. They are not doing the finite structure. They just take one unit cell and put a boundary condition. That means that it is going to infinity. We don't care. The boundary condition makes it infinity, but they optimize only one small structure. And the optimization which we apply here basically apply automatically everywhere.
One of the things of the class, of course, is a 2D surface because of the visibility. Is there any way that to have it like sort of have a third dimension in without really affecting visibility? I mean, if you have a freedom with going in the Z direction, maybe you can do more, but I don't know what's the impact on terms of
Z direction probability, the visibility will be an issue. Plus the kids and babies when they play, maybe it will.
You can do it on the outside surface.
Okay, I think a good thing, yes, can be. But then the problem also, when you have to deposit this thing and you have to make 3D. But it's a good idea, very nice, yes. With this sort of thing, we can actually achieve a lot of other things. They call it artificial magnetic conductors then. And then also become EBG, 3D. Now you can achieve not only one direction, you can achieve from here, very good thing. But maybe practically at the moment not possible, maybe in future. Maybe in future, yes.
Okay. You're doing you're not allowed. The guy who's doing video taping is not allowed. Please go ahead.
So, is there any criteria to select the coating surface? I mean, you are explaining about the copper material and how we select the coating material. So, what is the criteria?
Yeah, I think I showed you here one. It's a good question. Actually, you see here, because the criteria is this, that how much it gives you thermal blockage. See here, you see the copper. The copper is giving you about, if you start from 100 and go about here in this region, it's about 85%. Already the copper is stopping the heat. If I select cobalt or maybe ITO, you see they are not providing too much. So this is the This is one of the reasons why we select copper, because copper is already a very good insulator for heat compared to these two. So that's why we used the copper. That's why we did all these different measurements and found that the copper is the most suited. And when we put into the simulation, we actually did the simulation for others, but we found that the copper actually give us, you see, 0. You see here, this is ideal, actually 100% heat stop, which you cannot find even in the biggest company in the world. They make this energy saving glass, you will have about 70%, 80%. They cannot go beyond that. But in this case, you can go to 100%. The only area we are lacking here is this. But probably in Saudi Arabia, people will not mind if their windows are opaque. They don't want people to see in any way. You see what I'm saying?
Maybe they have the reason for small windows.
Yeah. So there is no problem at all. At the moment, even you can 50% visibility is still okay.
This is a single layer. I mean, when you do the coating.
Yes, single layer.
What about if somebody using multi-layer as in optics? You have to, sometimes some systems have 16 layers. More.
If they put 2 layers.
Expensive, and it is done. I know that.
Yeah, normally multi-layers are done for the soft coat. If they get with one glass, they receive, say they get only 70% efficiency. If they put another one, it will be 100%. But then, as you said, cost plus weight. You see, the glass weight is very big. So if I bring 3 layers here and put every layer here, it will be very, heavy. I remember one of my professors who was called like Einstein of Sweden. He was working with me, and he was picking with me, and his leg was broken because of this heavy glass. So then we thought, okay, it's better to stick with the single, because glass is very heavy material.
But these layers are actually in the very the micro wavelength.
Yes.
And you can do all type of filters.
Yes, we can do a lot of things in this. And one of the things for the graduate student, that this topic actually is, probably if you go IEEE summer search, you will find my name, because I have the one who started in Australia, and still I am going through this. And IEEE and other, where they have a paper on this, they send it to me for the review. So this is a very good field, and I have 2 PhD students, they are also working the same thing. There are a lot of things, like Professor Sagaf has mentioned. You see, there are so many opportunities there actually.
There
you can just take 1 point and you can do 1 PhD or 1 master's there. So.
Okay, good. Any more questions? Muhammad, use this one, please. That's what I think is.
First of all, thanks, Dr. Ghaffer, for this presentation. Now, regarding to remember about the passive element, this now is passive element. Some you have you designed before for active element by using fractal diode. You can use more frequency filters. Can for glass we do this one?
Yes, we can.
For active.
Theoretically, yes. But just imagine this size of glass, not like Professor Sagaf home. It's a very big one. On this one, and if you have 1 unit cell in microns, very small, and we have to put 4 diodes in one structure for E and F. If you have 4 diodes in one, imagine how many here if you multiply them. The cost and the power, almost, even in microwave regions, if you have an active FSS, it's a lot of big problems there. You have to be very careful about the power, DC voltage, how to give, the power dissipation in the diode. If 1 diode costs $1, and we have 20,000 diodes in that size of that TV screen, you have to spend $20,000 only on the diodes.
And the shape will be not good for.
Also the shape, how to incorporate this small diode within. So we have to find a technology. We cannot buy a diode from outside and put in that small size. So probably we have to find another technology to just put it, maybe built in some sort of thing. But that is good also, that if you don't want to go signal through, you just switch it on and everything block. But it will be quite difficult with this sort of.
Is this sometimes you have to call polarized glass?
Yes.
Sometimes you do it.
Yes.
You can block this.
Yes.
No scene.
Yes, that is correct. Yes. Maybe you can join me in this research. Allah, you have so many ideas.
Thank you.
Any more questions, please? Okay, thank you very much for this very interesting and enjoyable discussion. The nice thing I like today is that no single equation. Very good.
That's I have learned through the time. If I have a question, people will be sleeping down.
Yes, that's true.
So it's better to give
No,
the
no, it's
idea.
good, yeah. I think I like the way you presented the thing. I like the picture and the motivation. And I think the nice thing is that what we got actually, all of us, we learned a lot of things. We get a lot of things out of this presentation.
Also, doctor, you see, I do this YouTube shows, and we have learned that in a presentation of 1 hour, first 6 minutes, if you did not catch them,
They will sleep.
they will sleep. And in a YouTube 5-minute video, first 8 seconds, if you don't catch them, that's why I bring this data, the 2036, everything going down. So people stay, what's happening now? Then you can bring them to the, otherwise they will not be there. But anyway, thank you very much for inviting me. I'm very happy.
Thank you very much for giving this seminar, and thank you very much for attending. Assalamu alaikum.
Wa alaikum salam.